shown the
Good morning,
diagram
sir.
yesterday. Good morning. Good morning.
Good morning.
Yesterday we shown the diagram of anti-flotation chalk. Those anti-flotation chalks are below, and they are provided to prevent the tank floating off the bearing if it is holded. Because LPG will be in a liquid phase, and because of being liquid phase and your tank being separate, it is not integral part of the vessel's hull. So that tank is independent tank which can float off when your tank is flooded or when your LPG has leaked out. So there the thing can go off, the tank can go off from the outer surface, so it can float free. To prevent that float free, you have this anti-flotation chocks provided below. Now the tanks are constructed of notch ductile steel. So this notch ductile steel, basically, which we have done the grades of steel earlier, they are subjected to impact test at sub-freezing temperatures. So that's why it is notch ductile steel. Now the temperature operating here will be minus 43 degrees Celsius. And the boiling point, that is the boiling point of propane, because LPG is a mixture of propane and butane. So sometimes your LPG is 50-50, sometimes 30 for 70 propane and butane, and maybe opposite also. Propane can be 30 and butane can be 70. So the transverse bulkhead may be single or double. If they are double, then they are cofferdam type between cargo holes. And the insulation can be either on the tank or the secondary barrier of this type of ship. So I'll just show you the diagram again, the recapitulation. Now this is your self-supporting prismatic tank for LPG. So these are your anti-flotation chocks. So in case the LPG leaks out, it will be in fluid form. So this can get flooded and this can float free. To prevent that float free, you have this anti-flotation chock below here. You have a duct keel here. You have a whole space to contain the leakage. Then your water ballast tank and the hull. It can be double or a single hull. This is primary or this is secondary barrier. That is the primary barrier, the green color. The tank dome, the connections will be here. And this is your centerline bulkhead to reduce your free surface effects. Now, that was fully refrigerated one. Now we have semi-pressurized. The semi-pressurized or a semi-refrigerated tank. The capacity of semi-pressurized tank ranges from up to 5,000 meter cube. The cargoes carried are similar to fully pressurized. So you can carry propane and butane like that mixture. Independent type C are generally constructed of ordinary grade of steel. Now you don't have notch ductile steel here because this is temperature is -5 only. That was -43. So this is ordinary grade of steel and designed for a maximum pressure of 8 bar. So the earlier one was not even 1 bar. This is 8 bar. The outer surface of the tank is insulated, and then you have a refrigeration or reliquefaction plant. Cool the cargo. If it's trying to release a gas, then it can cool it down to liquid and maintain the working pressure. So that's why you have a refrigeration and reliquefaction plant. So this is a semi-pressurized LPG carrier. These are the tanks here because here they have to contain 8 bar pressure. That's why they are the tanks here. So the cargo tanks are often horizontal cylinders, which you can see. These are horizontal cylinders, and they are mounted on two saddle supports, mainly for incorporating bi-lobe tanks to have a better. So if you have single tanks, they combine to make a bi-lobe. I'll just show you how the bi-lobe is, so that you have a under deck space utilization. Now this is instead of you have these saddles here. So instead of two separate tanks and like you have in pressurized one now. Let's show you that also. Now in this pressurized you have two tanks here. So then you are not utilizing the space. But the pressurized, fully pressurized tanks you cannot have a bi-lobe because the pressure is 17.5 bar. So in case of semi-pressurized, the pressure is 8 bar. So when it is less than half of that, they can connect both the tanks and have a launchable bulkhead in between. So the under space utilization is more because these are semicircles now. So the under space utilization here, the cargo, the area lost is less. So that is beneficial to the ship owner because he is utilizing for the space. So this is semi-pressurized or semi-refrigerated LPG carrier. Now we come to the fully pressurized tanks. So the fully pressurized ships got a lot of pressure, about 17.5 bar. So the capacity cannot be large, which is less than about 2000 meter cubes or less of propane, butane, or anhydrous ammonia. They can also be carried in this fully pressurized tanks. And they carried in 2 to 6 uninsulated horizontal cylindrical pressure arranged below or partly below deck. So here there is no insulation there because there is no temperature reduction requirements. So no insulation is there, which you required insulation in a fully refrigerated and semi-refrigerated. So these independent tanks are normally designed for working pressure of up to 17.5 bar, and that corresponds to the vapor pressure of propane at 45 degree Celsius. So that's the maximum ambient temperature that a vessel is likely to operate. Suppose it goes to an area where your temperature is more than 45, maybe it goes to a Gulf country, then the deck cooling has to be started, otherwise your vessel can explode because it cannot take more than 17.5 bar pressure. And that is as per the 45 degree Celsius temperature, which is the vapor pressure of propane. So you have to do deck cooling to bring the pressure temperature down to less than 45 degrees Celsius. So tanks are constructed from ordinary grade of steel. They are all mounted on cradle-shaped foundations. And if they are below deck, then you have domes protruding through the deck to which your connections are fitted. Now the tanks are pretty long. Then they'll have FSC there. So they'll have wash bulkheads with perforations fitted in between. The shape of the tanks are preventing good utilization of underdeck space because here the underdeck utilization is less because they are all circular. So these spaces are lost, but they can't help it because they have to be fully pressurized to cater to 17.5 bar pressure. So the advantages of fully pressurized are that they are built with ordinary grade of steel as the cargo is carried at ambient temperature. There is no insulation required. There is no reliquefaction or refrigeration plant required as required by your semi-pressurized. Operations are more simpler because when the pressure is there, they don't have to maintain the temperature there. Disadvantage is there that due to the shape, the use of underdeck space is not utilized. Secondly, because it's got high design pressure requirements, then your tank wall thickness has to be increased. And that is going to increase the light ship weight and your dead weight will be reduced. So that is the problem with fully pressurized LPG carrier. So you can see this is a fully pressurized LPG carrier small ship where your tanks are protruding out. So the connections are on top. So that was LPG carriers. Now we'll be doing your LNG. Now LNG is liquefied natural gas. So that is carried at boiling point having minus 162 degrees Celsius. As LPG fully refrigerated was minus 43, this is minus 162. So the containment system has to be developed considerably basis your too low temperatures. So LNG carriers are fitted with independent cargo tanks or with membrane tanks. There are many types will be coming to it. How many types of LNG carriers are there? So the feature is almost unique to gas carrier as the cargo is kept under positive pressure to prevent air from entering the cargo system. So that means only the cargo liquid and cargo vapor are present in the cargo tank and flammable atmospheres cannot develop because when it is too rich, that you've seen the flammability diagram, you might have read it earlier, that when the cargo is too rich, the atmosphere is too rich with the flammable vapors, that it's not going to sustain any fire there. So the fire cannot develop there, or when it is too low, that is LEL, then the fire cannot develop. When it is in between the LEL and FEL, then the flammable vapors are there which can cause the fire to erupt. So all gas carriers are utilized closed cargo systems when loading and discharging with no venting of vapor being allowed, which you had for tankers. Now even that now they have come to vapor your VEC system that's on tankers and chemical tankers. That is vapor emission control as per Annex 6. So there also you don't have to open your PV valve in ports, and that is only for extreme when the pressure is high, then only it can release. Otherwise, all the vapor will be sent by vapor emission control lines to shore by that yellow lines. Have you seen that on tankers or not? We see the tanker guys. आप लोगों ने देखा है कि नहीं vapor emission control line on ship in tankers? None of you are in the tankers?
कैडेट शिप में किया था वीएलसी के
तो VLCC में तो रिक्वायरमेंट है, VLCC में तो रिक्वायरमेंट है वेपर एमिशन। हाँ वही है, रिटर्न लाइन इज VEC लाइन, उस पे लिखा होता है वेपर, येलो कलर होता है, स्टेंसिल किया होता है उसमें ब्लैक में।
जी सर।
हाँ उसका अलग मैनिफोल्ड होता है, क्योंकि ये सब आपको पूछा जाएगा ओरल में, व्हाट इज VEC, व्हाट इज रिक्वायरमेंट्स एज पर Annex 6, तो ये सब आपको पता होना चाहिए। मैं तो पढ़ाता हूँ ना सेकेंड बैच को, ये आपको पता होना चाहिए सारी चीज कि आपकी लेटेस्ट रिक्वायरमेंट्स क्या क्या है फॉर Annex 6, SEEMP क्या है, ये सब आपको पता होना चाहिए। EEDI क्या है, EOI क्या है, ये सब पता नहीं है आपको, तो पूछा जाएगा ये सारा ओरल में। ओके आगे करते हैं। So furthermore, all gas carriers utilize closed cargo systems. Where you're loading, discharging, and venting, nothing is allowed. In LNG trade, provision is always made for use of vapor return line between tanker and shore. इसमें भी होता है वेपर रिटर्न लाइन इन केस ऑफ एक्सेस प्रेशर. The vapor return line is there between ship to shore. So the shore authorities are going to charge you for that, and they want to make profit on that. So tanker में जो होता है vapor return line, उससे they can create lot of barrels of fuel per tanker. Super tanker अगर है VLCC, उसमें कई टन कार्गो बना लेते हैं with vapor return line, and they'll charge you for that collection. केमिकल टैंकर में थोड़ा मुश्किल होता है कि मे बी सो मेनी लाइंस आर देयर, तो आपके सो मेनी कार्गोज आते हैं, उसमें वेपर रिटर्न लाइंस कैसे करेंगे, दैट इज अ डिफिकल्टी. बट वीएलसीसी में कोई प्रॉब्लम नहीं, दैट इज हाइड्रोकार्बन गैस, तो उसको तो कलेक्ट कर ही लेते हैं. अभी इंडिया में नहीं आया है, इंडिया में दे डोंट हैव अ कलेक्शन फैसिलिटी, बट इन यूरोप एंड यूएसए ऑफ कोर्स वेपर रिटर्न लाइंस आर देयर. So the gas carriers have to comply with the standards of gas code or national rules, and with all your safety and pollution requirements common to other tankers. Safety features inherent to tanker design requirements have helped considerably in the use of the safety of these tankers. Equipment requirement for gas carriers. They're supposed to have temperature and pressure monitoring and gas detection and cargo liquid level indicators. And these are provided with alarms and ancillary instrumentation. So the variation equipment has made this gas carrier most sophisticated afloat today. And there is considerable variation in design, construction, operation of gas carriers due to variety of cargoes carried and number of cargo containment system utilized. So the cargo containment system may be independent, which is pressurized, semi-pressurized, or fully refrigerated, as we had in LNG. Plus, there will be a membrane type. So membrane type, दो type की हैं, we'll be coming to that also. That is a unique feature of LNG, the membrane type. अब ये वाला कौन सा टाइप ऑफ LNG कैरियर है, किसको पता है? सेकेंड मेट्स में इसका मिडशिप सेक्शन बहुत बार आता था, हिंट है, कौन सा टाइप का है?
मॉस,
हाँ, केवनर मॉस. So this is Kevlar Moss type B, independent tanks type B. The spherical tanks here. Now the cargo containment system and total arrangement is one is your primary barrier, the cargo tank, the secondary barrier fitted, then you have thermal insulation, then you have intervening spaces, the adjacent structures, all that will be requirement for cargo containment. Now the cargoes carried are at temperatures between 10 degrees to minus 55, so the tank hull may act as a secondary barrier. In that case, it may be the boundary of whole spaces. The tank types will be independent type, which is type A, fully refrigerated, independent type B, full typical LNG, which is Kevlar Moss, which we have seen, and independent type C, which is fully pressurized. And then you have membrane tanks, which is a unique feature for LNG ships only. So your independent tanks are normally completely self-supporting, and they don't form part of your tanker's hull structure, and they do not contribute to the hull strength of the tanker. So they are divided into A, B, and C, depending on the pressure design and the type of independent tank. We start with the fully refrigerated type A. Now these tanks are constructed primarily of flat surface. The maximum allowable tank design pressure is 0.7 bar. So that means the cargoes must be carried in fully refrigerated condition, which is normally below 0.25 bar. So the section we'll show is, this is a self-supporting prismatic tank requiring conventional internal stiffening. I'll just show you the diagram here. This tank. So it looks like your LPG, only the LPG there is a protrusion on top, rather than this type where there is not much a dome protruding out. Similar to of that LPG. तो थोड़ा सा फर्क है, LPG में थोड़ा ऊपर जाता है और ये थोड़ा subdued है. Otherwise everything else is same. You have anti-flotation chocks, you have insulation. You hold space, you have bulkhead, primary barrier, cladding, secondary barrier, water ballast. Only here the insulation is a different kind. Insulation here in this prismatic tank, you have glass fiber, you have stainless steel hull, there's a timber furring strip, inert space is there, glass fiber is here, plywood panel, balsa panels are there. The light, very light, balsa panel is very light and they're very good insulators. Then you have an aluminum tank inside, PVC foam seal between the balsa panels here.
Sir, what is that
So this is
cladding, sir?
क्लैडिंग क्या होता है कि क्लैडिंग वर्ड आपको अभी कराएंगे. क्लैडिंग का मतलब चिपकाना. स्टेनलेस स्टील टैंक होता तो क्या होता है? हाउ स्टेनलेस स्टील टैंक मेड? कोई आइडिया है? स्टेनलेस स्टील कैसे बनाया जाता है? टैंक जहाज में होता है ना स्टेनलेस स्टील टैंक, तो उसका मतलब टैंक प्योर होता है स्टेनलेस स्टील का क्या?
माइल्ड स्टील पे सर क्लैडिंग रहता है स्टेनलेस स्टील का.
हाँ, अब आपको बताते हैं क्लैडिंग क्या हो. क्लैडिंग का मतलब चिपकाना. अब वो तो गोंद से चिपकाएंगे नहीं, तो उसमें क्या होता है कि अभी आपको पढ़ाएंगे वो क्लैडिंग आपको पढ़ाएंगे जब आपको ज्वाइन करना होता है एल्यूमिनियम टू स्टील, ट्राई क्लैड बनाते हैं. तो सपोज ये स्ट्रिप है एमएस स्टील का और एक स्ट्रिप है स्टेनलेस स्टील का. अब इसके बीच में एक्सप्लोजिव्स लगाते हैं. यहाँ जैसे ये एक्सप्लोजिव लगाया, एक्सप्लोजिव माइल्ड एक्सप्लोजिव लगा, ज्यादा जबरदस्त वाले नहीं हो, टीएनटी टाइप के नहीं, बहुत हल्के वाले लगाते हैं एंड इसको एक्सप्लोड करते हैं. तो जब एक्सप्लोड करते हैं तो ये बड़ी हीट जनरेट होती है एंड दे गेट स्टक एंड फॉर्म अ क्लैडेड स्टील. तो ये क्लैडेड स्टेनलेस स्टील हो जाता है बिकॉज यू कांट रिमूव इट. फिर उसको प्रेशराइज करके जोड़ देते हैं. अदरवाइज आपका जो रबर कोटिंग होती है, जैसे ये आपका माइल्ड स्टील है और फॉस्फोरिक एसिड कैरियर है, तो उसमें रबर क्लैडिंग होती है. तो रबर को चिपकाया जाता है. दिस इज रबर एंड दिस एमएस स्टील, तो चिपका देते. तो दैट इज आल्सो क्लैडिंग. फिर आपका एक और क्लैडिंग होता है जब ट्राई क्लैड बनता है. तो आपका ये सपोज स्टेनलेस स्टील है एंड एल्यूमिनियम है और बीच में आपके ये लगाएंगे एक्सप्लोजिव्स और उसको उड़ा देंगे. हीट जो जनरेट होगी, एक सेंटर में मेटल बन जाता है, उसको कहते हैं ट्राइक्लैड. बिकॉज अदरवाइज इफ यू स्टिक योर स्टील टू दिस थिंग एल्युमिनियम, तो गैल्वेनिक सेल बन जाएगा और कोरोड कर देगा एल्युमिनियम को. तो इसीलिए क्लैडिंग करके एक नया स्ट्रक्चर बनाता है. तो क्लैडिंग इज ऑल जॉइनिंग. अब क्लियर हो गया? 3 एग्जांपल दे दिए, स्टेनलेस स्टील का, रबर का एंड एल्युमिनियम का. तीनों का दे दिया आप. Now in this example the tank is surrounded by skin of foam insulation जो दिखाया था. परलाइट क्या होता है? परलाइट इज अ मटेरियल व्हिच इज गॉट फ्रॉम वोल्केनोस. तो जो वोल्केनो इरप्ट करता है, दैट मटेरियल अंदर से निकलता है, दैट इज परलाइट. दैट इज वेरी लाइट एंड इट कैन बी यूज्ड इन इंसुलेशन. जैसे आपका प्यूमिस स्टोन मिलता है ना, आप पैर खुजलाते हो उससे, योर हील्स आर गेटिंग क्रैक, तो यू यूज प्यूमिस स्टोन. तो वो भी वोल्केनो से मिलता है. वोल्केनो से बहुत चीजें मिलती है. So material used in type A tanks is not crack propagation resistant. ये प्रॉब्लम है. क्रैक प्रोपोगेशन होता है जैसे आपका ब्रिटल फ्रैक्चर होता है तो क्रैक्स हो जाते हैं. सो दिस इज नॉट रेजिस्टेंट टू दैट. ये आपको अभी पढ़ाया था, नए बैच को तो अभी नहीं पढ़ाया, बट मार्च बैच दे नो अबाउट क्रैक्स. क्रैक से तो पता है ना कौन कौन से टाइप के. डक्टाइल फ्रैक्चर का क्रैक है, ब्रिटल फ्रैक्चर का क्रैक है एंड फटीग का क्रैक है. So propagation means how fast the crack will develop. Brittle fracture में the speeds are very very high. तो इसका ship suddenly sink कर जाएगा 2 मिनट में. In a fraction of second, fraction of a minute the ship will sink. MV Derbyshire नाम सुना होगा, sank in 2 minutes. कोई survivor नहीं. So that is because brittle fracture crack हुआ था. डक्टाइल फ्रैक्चर में बहुत टाइम मिलता है. फटीग क्रैक भी टाइम लेता है एकदम सिंगल, लेकिन एक बार वो क्रैक डेवलप हो गया, प्रोपोगेशन हुआ, तब फास्ट होता है, अदरवाइज फटीग क्रैक इज स्लो। ये क्रैक्स के बारे में यू शुड नो, बिकॉज इसके बारे में एग्जाम में दे आस्क। क्लैरिटी विल शुड बी देयर, बिकॉज रट्टाबाजी इसमें चलेगी नहीं। You tend to write something else about that answer. So therefore, in order to ensure safety, the unlikely event of cargo tank leak, a secondary containment system is required. That is the requirement for secondary containment system, because primary can leak, the secondary will control it. So the secondary containment system is secondary barrier. So that is type A liquid methane carrier. And as I explained, this is the insulation system for your type A fully refrigerated LNG. So the feature for all tankers with type A and tanks capable of carrying cargo below -10 degrees, secondary barrier must be complete barrier capable of containing the whole tank volume at a defined angle of heel and forms part of tanker hull. Now, the appropriate parts of the tanker's hull are constructed of special steel capable of withstanding low temperatures. An alternative is to build a separate secondary barrier around each cargo tank. So, the IGC code stipulates that the secondary barrier must be capable of containing a tank leakage for at least 10 days. The space between the cargo tank, which is the primary barrier, and secondary barrier, is the whole space that is for containing your leakage. So when a flammable cargo is being carried, these spaces are filled up with inert gas to prevent flammable atmosphere being created in event of primary tank leakage. So basically क्या है कि in this area जो आपको भी diagram दिखाते हैं, now this is your primary barrier, this is your secondary barrier. So the whole space is empty. But suppose you're carrying flammable gases and all, and suppose it leaks out, then this area becomes flammable. This can explode. So there's IG, not IG, inert gas. Inert gas can be nitrogen or IG generators where the moisture level is less than 1%. Not like your inert gas in tankers where your moisture level is 10%. Here the moisture level has to be less than 1%. So these are inert gas generators. So the different thing, they're pretty costly as compared to ones in tankers. So here the IG is filled up so that your tank leakage can be sustained and the flammable gases cannot erupt. So early LNG ships were fitted with self-supporting tanks of aluminum alloy having a centerline bulkhead. And then the balsa wood insulation. The balsa wood, as I said, is a very light wood that is a very good insulator. That was attached to the inner hull, and each insulated hold contained 3 tanks. So later vessels, they had prismatic tanks for better discharge capabilities, and the prismatic tanks had secondary barrier on top. I'll show you again why it is prismatic. Earlier they were flat like this, now they have made prismatic like this, the inner tank we're talking of. So the prismatic was aiding in discharge. Secondly, you could have your water ballast secondary barrier to offset your center of gravity here. So stability concerns also, like you have hopper tanks in bulk carriers. So the hopper tanks were there of water ballast in LNG for stability reasons also. Now we come to the Kevner-Moss system. So the independent type B tanks are constructed of spherical type, and they contain a containment system that is subject to more detailed stress analysis as compared to type A. And these controls must be including an investigation into the fatigue life and the crack propagation analysis. So you're supposed to have sensors to check any cracks there. Because if the cracks are there, you have to attend then and there. Otherwise, the crack propagation will start and it will create a havoc for the ship. So the most common arrangement in type B is your Kevner-Moss design. This is your Kevner-Moss design. So you have ballast space here, ballast space here. Then you have drip tray. The cargo pump is here, and the metal foil. And I'll show you more diagrams here. So here you have support skirt. This is a support skirt which allows your contraction expansion of your sphere. Otherwise, it will cause a crack. So the support skirt is made of high tensile steel to allow contraction and expansion. Then you have a bottom ballast tank here. And then you have structural transition joint here, this one. Pipe tower. So that's your pipe tower for pumping. A tank dome providing your penetrations on deck. Tank cover is of insulation, aluminum tank shell. Now that's the diagram here. You have support pillars here. So this is your skirt here. This is your stiffened skirt, which is allowing your contraction expansion. Then your insulation is there. The drip tray is there to collect your leakage, and the spray shield to prevent the liquid coming in this. So they all guide the leakage into the drip tray. So this is your insulation with splash barrier. This is the protective team steel dome. That's the cover, and these are the support pillars. So the cargo is carried like this. So that's the midship section of Kevner-Moss type, spherical type B. So this is a wireframe modeling of that, showing your counter columns, tank place, the skirt, and this is a deck here, foundation deck. Another 3D diagram here. So how it is placed on the cradle here. That's your tank. That's the pump. Pump is here. So it will come out here, and then you have the connections here. So that's a side view of the tanks. Now, because of the enhanced design features, tank B requires only a partial secondary barrier in form of a drip tray. The whole space in this is normally filled with dry inert gas, again for preventing flammable vapors being created in case of leakage. And we are adopting your modern practice. It may be filled with dry air also, provided that inerting can be achieved if vapor detection is showing cargo leakage. So that area can be of dry air. In case you have a sensor which detects cargo leakage, you will immediately fill in with dry inert gas. So this has to be less than 1% of moisture. A protective steel dome cover the primary barrier above your deck level and the insulation applied to the outside of the tank. So this design of type B spherical tank is typical of LNG carriers. You don't have this on your LPG carriers. So the sphere will contract and expand freely, and that will be compensated for the top half of the skirt, which is transmitting your stresses to the hull. So the outer surface of the sphere and part of the skirt is covered with polyurethane foam insulation. And the system is fitted with partial secondary barrier, which is drip tray under the tank, and splash seals at the side for guiding the spray towards the drip tray. Now, as per your type B notation, which is typical, each tank will be provided with sensors that will detect your leakage and also your cracks, so that your repairs can be done before your crack propagation starts. Now, the spherical tanks, as we had said, they do not use their available cargo space because a substantial part of hull is required to house your large spheres. And above the deck, your spheres are covered with weather covers. So that is your type B. Now we come to type C. So type C are fully pressurized. and these are normally spherical or cylindrical, and the pressure will be around 4 or plus 4, not like 17.5 we had for LPG. So the cylinders may be vertical or horizontally mounted, and the type of containment system is always used for semi-pressurized and fully pressurized gas carriers. Now, in case of semi-pressurized tankers, this can be used for fully refrigerated tanks, provided appropriate low temperature steels are used for tank construction. So Type C tanks are designed and built for conventional pressure vessel codes and can be subjected to accurate stress analysis. Furthermore, design stresses are kept low, and accordingly no secondary barrier is required for Type C, and the whole space can be filled with either inert gas or dry air, and for fully pressurized tankers can have normal air can also be allowed. So these are your fully pressurized Type C. So the domes are protruding out, the connections are on top. These are horizontal cylinders kept on cradles. You don't require secondary barrier here because this is pressure vessels, and they can sustain that kind of pressure. Now, the typical features of LNG carriers is membrane tanks, which is the next kind. So you have two designs, and they are two companies which had patented their type of design. One is Gas Transport and one is Technigas. Both are French companies. Now, the gas transport design has got a typical material alloy use, which is called INVAR. And that is 36% of nickel alloy. So that's used for both your primary and secondary barriers. Now, INVAR, which is nickel alloy, has got a very low coefficient of thermal expansion, and therefore you don't require any corrugations in the tank structure. For Technigas, you will have corrugations because that's made of stainless steel. For gas, you don't require any corrugations. Now, these sheets are very thin, very, very thin. So that's 0.5 to 0.7 mm thick. So it's almost 1 mm, 1 millimeter thick. So that's very, very light structure. And the insulation consists of plywood boxes filled with perlite. As I said, perlite is a material found in the volcanoes, which is a very good insulator. So this is your membrane tanks, non-self-supporting because they're part of the hull. Consists of thin layer membrane supported through insulation by adjacent structure. If the structural design is proper, the capacity is from that is 20,000 divided by 100. That's the capacity, and high production cost. This because they are very costly. So you have a water ballast here. You have an INVAR membrane, a secondary barrier. You have INVAR membrane as primary barrier. Then you have interbarrier between secondary and primary. Then you can have water ballast or void space on top. So this is the typical membrane tank. This is the actual tank here, the membrane tank, and this is your this can be a void space or water ballast here, the double hull here. That's again the membrane tank. You have tank dome. Walkways are here for inspection. Walkways are here for inspection. Those are your stringer plates. If I show you here, the stringer plates are here. So these are the walkways inside. That's your inner hull, access space, your support, ballast tank, insulation, a very thin insulation, the center line bulkhead here. These are the stringer plates here. This is again the membrane tank. So you have the hull, secondary insulation, secondary barrier INVAR is 0.7 mm thick, and that's insulation box is thicker, but the barrier INVAR is very thin. So if you see primary barrier 0.7, secondary barrier is also 0.7. Insulation box is thicker. So that's your inner deck and the side passageways. Then you have the discharge line and the pipe duct. Then the ballast tanks. Invar is 36% nickel alloy. Another diagram here. This is the pumping structure, stripping pump, foot valve, main cargo pump, filling line, emergency pump column, tripod mast, and the vapor dome under the discharge. So this is your plywood insulation in the gas transport, secondary membrane, primary membrane, and the Invar box, resin adhesive bonding rope, and the ship's hull. So this is the typical insulation system for gas transport, membrane tanks. Now we come to Technigas. Now Technigas are basically like this, stainless steel. All the corrugations are there. So they are all stainless steel. So they utilize stainless steel membrane system, which the tanks are constructed of corrugated sheet in such a way that they can contract and expand independently. Where membrane tanks, gas transport didn't have corrugation because they didn't allow contraction and expansion. So this forms the inner primary barrier, and balsa insulation is there. And then a secondary barrier similar is fitted to independent tanks like you had balsa foam system and all. Similar tank is in insulation is in Technigas. So here you have the primary steel membrane insulation panel, composite secondary membrane, inner hull, metallic insert, and the top bridge pad. That's your Technigas system. You can see the diagram here, the photograph here in the tank. The next kind is a semi-membrane, which is type B. So the type B tanks carry LNG cargo that has been used in a number of LPG carriers. So there's a rectangular box consisting of plain, unstiffened walls with moderate slope roof, rounded edges, corners that are not supported so that expansion and contraction is accommodated. So the tank is made of 15 to 25% thick aluminum alloy supported on layer of PVC insulation. The partial secondary barrier is made of plywood 25 mm thick, integral with PVC foam insulation. That is the same diagram. You have primary insulation, secondary insulation, composite secondary membrane, and top plywood. So that's the same for Technigas. So as a brief here, LNG is your type A, fully refrigerated. Type B, which is Kevlar Moss. Type C, which is fully pressurized. Then your membrane tanks, which are two types. This one is gas transport, and the next one is Technigas. So this diagram is of gas transport. So I'll show you a movie after the break for LNG and LPG, and then we'll start with shipbuilding, the next class. So 2 minute बचे हैं. Any questions? Any questions now?
Sir, one question.
हैं? हाँ पूछो.
Sir, the tank layers, they are cladding, they are layered. Aluminum is layered over stainless steel. So both have different
Correct.
expansion ratios.
The thing is, जब cladding होता है, the material inside, because you see aluminium जैसे cladding होता है, तो MS steel अब aluminium हुआ और steel हुआ, ठीक है. Suppose you have, अब जैसे आपको पढ़ाएंगे अभी कैसे you join aluminum to steel, so your steel will have a different expansion ratio, aluminum will have different expansion ratio. In between you will have a tricard layer, will have its own expansion ratio, so that will match. जब join कर रहे हैं वो एक और metal बन जाता है ट्राइक्लाड, उसका expansion ratio unique हो जाता है, तो फिर वो match कराता है दोनों से, because it has been fused with steel and aluminum, तो उसका अपना expansion ratio है. Otherwise क्या crack हो जाएगा. Now because of that fuse, it will not crack. And similar thing with stainless steel and MS steel. Join कर जाता है, so that way वो काम. चलो, we'll have a break now. and then we'll come back in about 15 minutes. Okay, that time we'll 15 मिनट का ब्रेक ले लेते हैं.